Imagine an entire planet made of diamond. We're not talking about a rare gem hidden somewhere in space, but a real planet, far beyond our solar system, with features so bizarre they sound like science fiction. Its name is 55 Cancri e, and what astronomers have discovered about this world is absolutely mind-blowing. Extreme temperatures, an eerie inner glow, and a composition that could rewrite what we know about how planets form. But is this planet truly made of diamond? How do we even know that? And here's the big question. Could we ever visit it or tap into its unimaginable wealth? In this video, you'll dive into one of the most fascinating mysteries of modern astronomy, an exoplanet that shines like a jewel and might be hiding secrets far beyond its glittering surface. Imagine a world where sunrise never comes, where the heat is so intense it turns rock into vapor, where the ground might be hiding layers of pure diamond beneath oceans of molten lava. This is 55 Cancri e, one of the most extreme exoplanets ever discovered. Cancri e lies about 40 light-years away from Earth in the constellation of Cancer. It orbits a star called 55 Cancri e, a yellow dwarf similar to our Sun, but with a much more intense cosmic temperament. And the first thing that catches attention is its orbit. While Earth takes 365 days to complete one lap around the Sun, 55 Cancri e does it in just 17 hours and 40 minutes. That means it's so close to its star there's barely any room between them. Just 2.4 million kilometers, less than 2% of the distance between Earth and the Sun. This insane orbit puts the planet in a state of constant thermal torture. The star-facing side is bombarded with relentless radiation. Temperatures can soar above 400 degrees, 2400 degrees, hot enough to vaporize iron, silicon, and just about anything else. The dark side, permanently in shadow, is slightly less chaotic, but still exceeds 1800 degrees, 1000 deg. This massive temperature difference suggests the planet is likely tidally locked, meaning it always shows the same face to its star, much like how the moon always shows the same side to Earth. But what truly intrigues scientists is its composition. With 8 times the mass of Earth and nearly twice its diameter, 55 Cancri e is classified as a super-Earth. Too massive to be just rocky, too small to be a gas giant. Its density suggests a massive metal-rich core surrounded by thick layers of exotic rock. And here's where it gets fascinating. The planet might be rich in carbon. Spectroscopic studies and modeling hint that the interior of 55 Cancri e could contain enormous amounts of crystallized carbon, in other words, diamond. Not a solid diamond planet, of course, but possibly one with vast layers of graphite and diamond formed under intense pressure. This led some astronomers and science outlets to nickname it the Diamond Planet. But in reality, its surface might be far more violent than glamorous. There are strong indications that the surface is covered in molten lava, constantly renewed by stellar heat and internal geological activity. Simulations suggest the day side could be a literal ocean of boiling magma, while the night side forms crust-like slabs of cooling basalt, cosmic lava plates teetering on thermal collapse. Another major mystery, its atmosphere, or the possible lack of one. Infrared data from telescopes like Spitzer and Hubble show signs of heat retention, but the results fluctuate wildly. Sometimes the planet glows intensely in infrared, other times it dims. This points to a volatile and dynamic atmosphere, possibly made of hydrogen, helium, carbon dioxide, or even vaporized minerals like sodium or potassium, boiled off from the surface. And there's one more twist. 55 Cancri e emits more heat than it receives from its star. That means something inside is heating it up. One likely cause is tidal heating, the planet being stretched and compressed by gravity, like Jupiter's moon, Io, which experiences non-stop volcanic activity thanks to gravitational tug-of-war. In short, 55 Cancri e is an anomaly. A scorching, dense, carbon-rich world, potentially diamond-stuffed and lava-covered. It's a natural laboratory of cosmic extremes, and yet, somehow it's survived in this hellish orbit for billions of years. It's a place that defies everything we thought a planet could be. The surface of 55 Cancri e is not just a solid, static crust, but a battleground where cosmic and geological forces collide in a constant spectacle of destruction, and creation. Its absurd proximity to its star, 55 Cancri A, results in heat so intense that the planet's crust isn't just solid land, but is constantly being melted and reshaped under the relentless forces of volcanic activity and radiation. On the star-facing side of the planet, temperatures soar above 2,400 degrees Fahrenheit, exceeding the melting points of metals like iron and nickel. This creates an environment where any matter approaching the surface instantly liquefies, turning the planet into an ocean of molten magma. But unlike the tranquil seas we are familiar with, this magma is not still. It flows, it churns, and over time it forms ever-thickening layers of molten rock and gases, creating a constantly changing landscape. Because of this intense heating, the crust of 55 Cancri E isn't like Earth's stable solid surface. Instead, it's a dynamic, ever-changing shell, constantly reshaped by the immense internal pressures and the continuous bombardment of radiation. The interaction between these forces causes the planet's geology to constantly evolve. The rocks that form never stay the same for long, as they melt and re-solidify in a never-ending cycle of renewal and destruction. As the molten lava cools, it solidifies into large basalt plates, but these plates are not immobile like those on Earth. They float and shift, driven by geothermal activity that constantly reshapes the surface. In some areas, the crust is thin enough to allow magma to rise, forming temporary islands of solidified rock. These islands, while impressive, have a short lifespan, as they will eventually melt away and rejoin the fiery sea of lava. The immense pressure inside 55 Cancri E is also a noteworthy factor. Below the surface, where temperatures continue to increase, the forces of compression cause carbon to transform into graphite and possibly even diamonds. This process, much like what happens on Earth, occurs under conditions of extreme pressure and heat. But the conditions on 55 Cancri E are far more intense, and this results in layers of carbon crystallizing into diamonds deep within the planet. These diamonds would not form the kind of diamond planet we once imagined, but instead, they would be buried layers of carbon, formed over billions of years under incredible heat and pressure. The planet's metal-rich, carbon-heavy interior is likely the key to its unusual density. With a mass 8 times that of Earth and nearly twice its diameter, 55 Cancri E is too massive to be entirely rocky, but too small to be a gas giant. Instead, it's a geological oddity, with layers of rock, metals, and carbon crystals unlike anything we've encountered elsewhere in the solar system. Moreover, the volcanic activity on 55 Cancri E is not like anything we see on Earth. The planet's crust is continuously renewed and destroyed in a much more frenetic cycle than we observe on other rocky planets. The immense internal pressure causes magma to be expelled with tremendous force, resulting in near-constant eruptions and fissures that release gases and materials onto the surface. These materials may include heavy metals and minerals like silicates, but also vapors of elements that have been vaporized due to the extreme heat, such as potassium, sodium, and even more exotic minerals. But how does this affect the planet's landscape? The crust exposed to space on the night side of the planet likely looks completely different. Unlike the day side, where heat is constant and intense, the night side undergoes a cooling cycle that causes large cracks in the surface. These fissures expand over time, creating an unstable terrain where thicker crust may crack open, exposing the underlying magma in a continuous process of healing the planet's wounds. In this chaotic environment, the planet is in a constant, tectonic crisis. There is no rest between cycles of transformation. Everything is in constant motion, and the crust is like a sheet of molten copper, melting and regenerating as the forces of the universe play out in a spectacle of heat and pressure. The atmosphere of 55 Cancri A remains one of the most fascinating and puzzling features of this exoplanet. Its composition and behavior are anything but predictable, shaped by both external and internal forces. Given the extreme conditions on the planet, its atmosphere is not a stable, uniform layer, but a dynamic, volatile mix, continuously shifting under cosmic pressures. The first key factor influencing the atmosphere is the extreme heat generated by the planet's proximity to Its star, 55 Cancri A, located just 2.4 million kilometers from its star, a mere fraction of Earth's distance from the Sun, 55 Cancri E faces relentless radiation. On the day side, temperatures soar above 2,400 degrees C, which means that any substances present in the atmosphere are constantly vaporized. While scientists initially expected the planet's atmosphere to consist primarily of hydrogen and helium, observations from telescopes like Spitzer and Hubble show a far more erratic pattern, fluctuating heat emissions, which suggest a much more chaotic atmospheric environment. This variability is driven by two main factors. First, the planet's extreme proximity to its star causes uneven heating, with parts of the atmosphere heating and cooling at different rates. This results in thermal separation, where lighter elements escape into space and heavier ones accumulate in the lower layers. Secondly, the intense solar radiation causes chemical reactions, breaking down more complex compounds like carbon dioxide. This results in the release of reactive elements like carbon and oxygen, creating a highly unstable atmosphere compared to what we see on Earth. Moreover, the strong solar winds from the star likely play a role in stripping away lighter elements from the atmosphere, particularly hydrogen. This process, known as atmospheric escape, is common in planets close to their stars. Even with a strong gravitational field, the extreme heat and stellar pressure create conditions where the atmosphere is constantly being shed, preventing the retention of gases. Another intriguing question is how the presence of heavier elements, such as carbon and silicon, affects the planet's climate. It's possible that vaporized carbon forms layers within the atmosphere, which interact with infrared radiation from the star. This could create an uncontrollable greenhouse effect, raising temperatures even further. However, the rapidly changing nature of the atmosphere means that these gas layers could exist only temporarily before being stripped away or recombined. There is also the possibility that the planet's atmosphere is very thin, or that it has a protective layer that is extremely fleeting. As heavier gases like carbon dioxide are rapidly released and recombined due to heat, the planet could be left with a transient atmosphere, one that is constantly changing and adjusting. Models suggest that, unlike Earth, where a stable atmosphere traps heat consistently, 55 Cancri's atmosphere behaves more like a chaotic system, with gases accumulating and dissipating in short cycles. Infrared studies indicate that unlike planets like Earth where heat is retained relatively evenly, 55 Cancri E exhibits interruptions in its thermal pattern. This means that the heat absorbed is not distributed uniformly, and the lack of a consistent atmospheric structure contributes to unpredictable temperature fluctuations across the planet. As a result, 55 Cancri E could have a very thin atmosphere, or one composed of more volatile gases that are constantly vaporized and replenished. This unstable, fleeting atmosphere is part of what makes 55 Cancri E so unique. Its environment is in constant flux, driven by both external stellar radiation and the planet's internal geological activity. Instead of a thick, stable atmosphere, it has a volatile, ever-changing mix of gases, constantly being stripped away and replenished. This dynamic nature contributes to the planet's extreme and unpredictable climate, further solidifying 55 Cancri A as a place of cosmic extremes. 55 Cancri A isn't just a planet of extremes. It actually influences everything around it. With its significant mass and incredibly close orbit, it exerts a real gravitational pull on the other planets in the system, subtly shaping their paths. This interaction creates what scientists call orbital resonances, a kind of gravitational dance that keeps the system in balance. Another twist, the 55 Cancri system is binary. There's a second, distant companion star, 55 Cancri B. Though faint, it may have played a key role in shaping the system's architecture, possibly even nudging 55 Cancri E inward toward its deadly orbit in a process known as planetary migration, and, because of its strange behavior, 55 Cancri E has become a scientific benchmark. Astronomers use it to test and refine observation methods like spectroscopy and light curve analysis. So beyond being a hellish world, it's also a natural cosmic laboratory, helping us decode how alien planets form and evolve. The idea of 55 Cancri E being a diamond planet made headlines everywhere. But within the scientific community, it's still a hot debate. The diamond theory came from a mix of density and temperature estimates, not from direct evidence. So far, no telescope has detected any spectral signature of diamond on the planet. What we have are simulations suggesting it's possible if the planet formed in a carbon-rich, oxygen-poor environment, a rare but plausible condition. However, recent observations show unusual thermal fluctuations on the planet's surface, likely caused by escaping gases or elements that don't match the behavior of exposed diamond crusts. Even if diamonds exist deep within, it's unlikely they dominate the outer geology. There's also a rarely discussed point. Diamond has extremely high thermal conductivity. If large regions inside 55 Cancri E were made of diamond, heat would spread differently. But infrared readings show a thermal behavior that contradicts that idea. In the end, the diamond planet nickname is more media myth than confirmed science. But it did something important. It got people talking about a planet that pushes the limits of everything we thought we knew. Want more mind-bending alien worlds like this? Hit that subscribe button, drop a like, and stay tuned. The universe is just getting started.